Okay, the next question is question 5, 2002. X-rays are commonly used as an imaging technique in medical diagnosis. The spectrum of X-rays from an X-ray tube shows two components, a continuous background radiation and a line spectrum. Explain the physical principles of the production of each of these elements. Now I'm just going to draw that for a wee second at the side. What you have whenever you have X-rays produced, this is their energy and this is their intensity. In other words, the number of them. And you have this kind of continuous spectrum, which is kind of like that. And then you have these wee spikes on it. So this part here is a continuous spectrum, and these parts here are the line spectrum, or the wee spikes that are shown on the spectrum. Sometimes you might have them over here too. It depends on the element that you're using. So this is really basically the basic. Explain the physical principles of the production of these two components, and there's 5 marks. Now, what I think there would be 2 marks for the first part and 3 for the second. Again, I don't have a mark scheme for this particular year, so that's why I'm going to divide up the answers. So first thing is explaining how X-rays are actually produced. So again, you've met this before, and you will meet this question again. You have electrons, and again I'm just going to write in bullet points because I haven't much room, are accelerated across an evacuated tube or a vacuum. And hit an anode, which is usually made of tungsten. This decelerates them. And then they give out. So I think that's 1 mark there. They then give out energy. So when they're decelerated, they lose energy. And it has wavelengths in the X-ray region of the electromagnetic spectrum. Okay, so your writing of course will be much smaller than that, and you've plenty of room, and you can fill in the rest of the page right down to the bottom. So that would be 2 marks. And this produces X-rays with a range of wavelengths as different electrons hitting the target are decelerated by different amounts. Okay, so I think I've actually got myself a 3rd mark here, and that causes a continuous spectrum. So I've actually got 3 marks here for the continuous spectrum bit. So this is what happens. I'll give you the ticks here. And then there's your 3rd one there. Now, this is what happens when you have electrons going across a tube and hitting the anode. They have the same amount of energy when they leave the cathode, but when they hit the anode, they give up different amounts of energy. And when they do that, if there's different amounts of energy available to create X-rays, then those X-rays are going to have different amounts of energy themselves, and so they can have energy from here to here. The X-ray photons that are given out have different amounts of energy. Most of them are found around the middle there, and that's why the intensity is greatest there. Around the middle, they give up, an average, like some kind of average amount of energy, and very, very few of them give up all their energy or their maximum energy, or their maximum kinetic energy, and that produces, when they do that, that produces X-ray photons with a maximum amount of energy as well. Okay, so we'll just go through that again. Electrons are accelerated across an evacuated tube. So you've got, I wonder, should I draw that? And maybe we'll draw this. I'm going to draw it down at the bottom here. You've got a cathode here. You've got your electrons being accelerated across. They hit then an anode. And when they hit the anode, what they do is they give out different amounts of energy. Or they give out X-rays with different amounts of energy. This depends on how much energy, kinetic energy, they lose when they hit the anode. And that's why you get a whole range of energies. Now, the line spectrum are created when some of the electrons are going across a tube. So they hit the target, which is the anode. And cause excitation of inner shell electrons. So if I just drew away, if that's the nucleus of an atom, and there you've got electrons in shells, as you'd have met in chemistry before. If you have a photon coming in here, let me get a red pen for you. If you have an electron coming in here, and it hits one of these inner shell electrons, and it moves up to an upper layer, then it's unstable, but for a very brief period of time, and then it comes back down again. And when it does that, it gives out the energy it had absorbed. So it absorbs energy from the electrons coming in which hit it. This is your material of your target, probably tungsten, or your anode there. Okay, so this is one of your atoms of your anode. Electron comes across the tube, hits an inner electron, it moves to a higher energy level for a very short period of time, goes back down to where it came from, and it gives out energy in the form of an X-ray. But there's very, very few of those, and they're it's very, very specific amount of energy that's given out there, and that's why these lines occur on the spectrum at set values. You know, they would have down here, if you looked at your scale, that those would correspond to the difference in energy levels between one shell and another, and that's why they're very, very specific. So then the electrons which have been excited then will return to inner shells. Giving out energy in the form of X-rays with very specific energy values. Okay, so that's how you have, first of all, your continuous spectrum, but then this is how your line spectrum is created, and there will be 2 marks there. Okay, and that's your 5 marks in total. The next part